Before starting this video, let me ask you something. When you do classification tasks, you use Bernoulli distribution. When you do regression tasks, you use Gaussian distribution. And when you model the count data, you use the Poisson distribution. So, three different problems. So, three different distributions, right? No, wrong. Actually, the only difference is they use different parameters and they measure different things. They look different, they feel different, and most courses treat them as completely separate things. There's one single formula that all of them come from, and once you see it, you will also understand something else, which is why the sigmoid function looks exactly the way it does, because it wasn't invented, it was derived, yes, from the probability theory. First, we'll set today's agenda, which is understanding the exponential family form, and then we will see the origin of sigmoid function. Yes, so what is exponential family form? This single formula represents the exponential family form. Yeah, I know it looks a little bit intimidating at first. So let's just go piece by piece and I promise it will make sense quickly. So yeah, the first thing is eta, the natural parameter. Or you can also say it as the canonical parameter. Think of it as the D version of your usual parameter. Instead of working with the mean or the variance directly, we work with the transformation of them. We will see exactly what that looks like in a second. Till then, the next thing is Tx, which is the sufficient statistic. This is the part that actually captures the information you care about from your data. For simple distributions, Tx is nothing but x itself, where x is the data point itself. And for complex ones, like the Gaussian, it's a vector. Next is hx, which is the base parameter. It's a function of x that doesn't depend on eta at all. Think of it as a shape that sits underneath everything, like a background layer. And finally, a eta, which is the log partition measure. It's nothing but the normalizing constant written in log space that keeps everything summing up to 1. This one is going to do something magical later. Till then, we will understand how we can write a of eta. It is log multiplied by integration of hx dot exponential raised to power eta transpose tx dx. You don't always have to compute it by hand, but knowing what it is will unlock a lot. Okay, let's now verify all of this actually works. Let's take two distributions first and show they fit the form. So our first distribution is the Gaussian distribution. We will see that the Gaussian distribution is a part of exponential family form itself. We know that we can write Gaussian distribution as px, mu, sigma square equals to 1 upon root 2 pi sigma square dot e raised to power minus x minus mu whole square upon 2 sigma square. We will expand x minus mu whole square and we get x square minus 2x dot mu plus mu square. So the power of exponential becomes minus x square upon 2 sigma square plus mu dot x upon sigma square minus mu square upon 2 sigma square. Hence we get our exponential family form as px comma eta equals to 1 upon root 2 pi dot e raised to power mu upon sigma square comma minus 1 upon 2 sigma square dot x comma x square minus mu square upon 2 sigma square plus log sigma. Now very carefully look at that. We can say this term as eta, this term as tx, and this whole term as a eta, and this term as h of x, as they all satisfy the definitions of these parameters we discussed before. So the final equation becomes hx dot e raised to power eta transpose tx minus a of eta, which is nothing but the exponential family form. So now let's understand how Bernoulli distribution belongs to the exponential family form. Plus, in this only part, we will understand how sigmoid function originated, which is the most important part of this video. Yeah. So we will start from very basic. we know that Bernoulli distribution is written as px comma phi equals phi raised to power x 1 minus phi raised to power 1 minus x, where x belongs to 0 comma 1. Phi is just the probability of getting a 1, like the probability of heads on a coin. X is either 0 or 1. Now the formula looks completely different from Gaussian, but watch. All we are going to do is take the log, rearrange and put it back inside the exponential. That's the trick. So px comma phi equals exponential of x log phi plus 1 minus x log 1 minus phi, which can be written as x log phi upon 1 minus phi plus log 1 minus phi. We just use the fact that phi to the power x is the same as e to the power x times log phi. That is just the definition of logarithms. And then we collected the x terms together and factored them out. Now look, this is already in the exponential family form. How? Look at this. We can say that log phi upon 1 minus phi is eta, which is the natural parameter, log odds, or you can also say that this is your logit function. This is your tx, and this whole thing is your a eta, or we can write it as a eta equals minus log 1 minus phi, which is equal log 1 plus e raised to power eta. We did this thing to satisfy our definition of exponential family forms as we discussed before in the video. And for hx, we know that here is a 1, which we can say as hx. As we discussed before, eta here is the log of phi over 1 minus phi. Now, here's the part that's going to surprise you. What if we go backwards? What if we start from eta and ask what is the probability phi? So this will give you the answer for how sigmoid function came into existence. Let's see that. We take eta as log phi upon 1 minus phi. Then we take the exponential both sides and we get this. We multiply both sides and we get this. Then we rearrange the terms and we get this. And finally we get our phi as e raised to power eta upon 1 plus e raised to power eta. What is this? Let me rewrite this as 1 upon 1 plus e raised to power minus eta. Now you know this? Yes. This is the sigmoid function or sigmoid activation function. Actually, we did not design it. We did not say let's pick a function that squishes things between 0 and 1. We just asked, if your data is Bernoulli, what is the natural parameter and how do you convert it back to a probability? And the answer that falls out is exactly the sigmoid function. So every time you use logistic regression, what you are really doing is fitting a linear model in the natural parameter space, which is the log odd space of the Bernoulli distribution. The sigmoid is just the conversion back to probability. That's the whole story told properly. Now we'll learn something about the log partition miracle, which is the A eta miracle means free moments. Okay, now let me show you something about A eta that looks almost too good to be true. So far, A eta has just been the normalizing constant, the thing that makes everything add up to 1. That sounds pretty boring, right? Just a technical requirement, but it's hiding something incredible. Let's see that. Gradient of A eta with respect to eta is expectation of Tx, means the gradient gives us the mean of Tx. Again, if we calculate the gradient of A eta with respect to eta again, we get the covariance of Tx means double gradient or Bayesian gives us the covariance of Tx. Now what about this? The gradient of A with respect to eta gives you the expected value of sufficient statistic, which is Tx. And the second derivative, the Bayesian, gives you the covariance of sufficient statistics. In plain English, if you want to know the mean of your data, you don't need to integrate. You just differentiate A. Let me show you exactly why this works. A eta is log of log integration hx dot e raised to power eta transpose tx dx, as we discussed it before. Now let z of eta as integration hx dot e raised to power eta transpose tx dx. Hence, a eta is nothing but log z eta. Now, if we calculate the derivative of a with respect to eta, we'll get 1 upon z dot derivative of z with respect to eta, which is 1 upon z dot integration of tx dot hx dot e raised to power eta transpose tx dx, which is again equal to integration of tx dot px comma eta dx, which is equal to expectation of tx. All we did was differentiate inside the integral, a standard calculus move, and then we noticed that what is left is exactly the definition of an expected value. The Bayesian follows by doing it one more time, and you get is the variance. So Gaussian A eta equals to mu square upon 2 sigma square plus log sigma. We calculated it before. If we find the gradient of A with respect to eta, it gives back what? Mu square comma sigma square plus mu square, which is equal to expectation of x comma expectation of x square. So for the Gaussian, differentiating A gives you back exactly the mean and the second moment. No integration needed, just calculus on a scalar function. This is why the exponential family is so computationally powerful. Computing moments is normally painful. Here, it's just differentiation. Why all this matters in machine learning? Let me connect it to things you already use. First is generalized linear models or GLMs. You use linear regression, which is from the Gaussian family. You use logistic regression, which is from Bernoulli family, and you use Poisson regression, which is from Poisson family. Moreover, all GLMs linear model in eta space exponential family output. Every generalized linear model, be it linear regression, logistic regression, or Poisson regression, assumes that the output follows some exponential family distribution. The linear part, xw, lives in the natural parameter space, and the link function, like the sigmoid, converts from that space back to something you can interpret as a probability or a count. They are all same model, just with different distributions plugged in. Now, second is maximum entropy principle, which means exponential family equals to maximum entropy distributions. Of course, they are subject to some constraints on expectation or mean of Tx. There's a theorem that says if you have some constraints on what the expected value of your data should look like, and you want to pick the distribution that makes the fewest additional assumptions beyond those constraints, the answer is always an exponential family distribution. This is called the maximal entropy principle. So you are not using Gaussian because it's convenient. You are using it because, given what you know, it's the most honest distribution you could pick. Now the last is conjugate priors. Every exponential family has a conjugate prior in same family. Bayesian updates are tractable. And finally, in Bayesian inference, if your likelihood comes from the exponential family, you can always find a prior such that the posterior stays in the same family. That means Bayesian updating has a closed form solution. No intractable integrals, no approximations needed. This property, conjugacy, is an exponential family result. It's not a lucky coincidence for specific distributions. It's a guarantee that comes with the structure. So lastly, here's the big takeaway. Every time you pick a distribution in an ML model, you are picking a member of this family only. Every time you write down a likelihood function, you are working inside this structure, whether you know it or not. Now you know it, of course. And the sigmoid function, it was never an invention. It's just what the Bernoulli distribution looks like when you do the math properly. Now you know where it actually comes from. So, in the next episode, we are shifting gears to linear algebra. Everyone teaches you how to compute the SVD. Nobody teaches you what it means geometrically, what it means to rotate data, stretch it, and rotate it back. We are going to fix that, and you will understand why PCA works at a level that goes way beyond the formula. So, see you there.